been covered so far. And I will use some objects which were called T-branes and were introduced in the context of Earth theory, and try to relate them to black holes. Try to extract some information about black holes out of T-branes. So this is work in progress, which is done with Josef Bena, Johan Balabak, and Raffaele, who's in the audience. So let me start by giving some introduction. So we know that the entropy of the black holes is in general one of the big mysteries of quantum gravity. Generally, it's something that is very difficult to understand, and classical GR really fails here. So in string theory, starting from '96 with the construction of the Strominger-Alpha black hole, we learned that it's actually possible to count the microstates of the system and therefore obtain the entropy. So you have a way to actually to account for the entropy of the black holes once you embed it in the string theory. So the main problem is that for instance, you can try to look at the extremal black holes in 4 dimensions. Here the counting is more difficult to understand. One way to see is that if you take the near horizon region of the black hole, it has a factor that it's an ADS2. So we don't have actually a well-defined holography for ADS2. This would be a sort of quantum mechanical system with some sort of conformal theory, if you believe in general in this. And you don't have it in general for microstate counting. So this system is a little less understood. So what we want to propose, at least, is that one can try to use some systems like T-branes. T-branes were introduced in the context of Earth theory for phenomenological reasons, but what we observe is that using T-branes, you can try to construct some states that, once extrapolated as strong coupling, should correspond to microstates of the black holes. So this leads to a way to say that possibly a dual description for this kind of black holes could be given by matrix models, in particular the BFSS model, that was introduced back in the 90s to give a description, a full description of M theory. So let me highlight the strategy that one has in mind once this kind of computation is done. So usually you have D-branes in string theory. We understand them very well. But we can have 2 different dual descriptions. One is done in terms of open strings, and the other one is once you look at the supergravity solution. And the first one works very well when the 't-Hooft coupling of the gates theory is very weak, which is in string theory is given by GS times n, where n is the number of D-branes. But once you extrapolate to strong coupling, actually it's a supergravity solution that works much better because the curvature of the solution becomes smaller, and actually some configuration of D-branes can actually turn into black holes. So the general strategy that was already followed by Strominger and Alpha is to use this side of the duality to count microstates, and actually the counting and the extrapolation to the gravity side is possible because you have protections. These are BPS states. On the gravity side, people started, since this first observation, also to look at what the microstates can be. You can try to construct gravity solutions that are dual to the microstates and understand what are the properties. But for this talk, I will always remain on the left-hand side, at least for our construction. So Just to put this in more concrete details, so I will talk about how supergravity black holes look. The general answers for a D-branes, at least in supergravity, has a metric that has this form. So you have some coordinates that are parallel and orthogonal on the whole volume and transverse. And you have some warp factor, which this is the form at least for branes that are smaller than 7 branes. And there are other fields. They are important, like Ramon-Ramon potentials and the dilaton. They are important, but I did not copy them here, just for simplicity. So if you look, the warp factor actually vanishes at r equals 0. So you can say that the solution has a horizon. But the main problem is that if you try to take this solution, the horizon you find when you compute it in the Einstein frame is actually 0 area. So you need something more complicated. You can try to put some different kind of branes at the same time in the game, and this actually gives a solution with a finite area for the horizon. So you would call this actually a genuine black hole. So this would be like an extremal Reiser-Nordström black hole. For instance, in 5 dimensions, you need at least 3 different charges to find finite area. And the first example, which was the one by Stronger and Waffa, would be D1, D5P. And there are, of course, these have been generalized also, but in this case, the near horizon geometry, if you look at it, is ADS3 times S2 times X, where X is some compact manifold. You can take it to be K3 or T4 for this kind of construction. And so if you notice here, you have an ADS3 factor, and you can understand the theory, which is the one on the strings living at the intersection. This gives the CFT dual. And by looking at the CFT dual and how the number of states grows with the fixed charges, you can actually count the entropy of the black hole, number of microstates. So the kind of system we have in mind is actually 4-dimensional. These are black holes that preserve n equals to 1 supersymmetry. And this is necessary to have a finite area. Here you need 4 different charges. So you have D0, and 3 different D4s. So the important part is that these D4s will have triple intersection, which is not 0. It will be 1 point in the compact space. For our purposes, we will make a local description of the system, and one can try to compactify, for instance, on tori. So this kind of states would be 1/8 BPS states in n equals to 8 supergravity. In principle, with the kind of construction we will be doing, we can construct more complicated solutions. But we want to focus on this one, which is sufficiently simple. So if you look at the near horizon geometry, you actually can see that you have an ADS2 factor, as I said before, and that the area is the product of the 4 charges. So if you turn off one, actually, you see that the area goes to 0. So this will be, again, a genuine black hole in n equals to 8 supergravity. So now I will go to the other part. I will talk about T-branes. They were introduced in F theory. So I will take, for T-branes in general, some brane configurations where the scalar fields that describe the position of the branes are taken on commutative values. So, for example, one can try to do this for 7 branes, wrapping a complex curve or a complex surface. So the case of the curve would be a 6-dimensional case. You have a gauge theory in 6 dimensions, or a surface you have in 4 dimensions. So the first case, you have this kind of supersymmetry equations, which were found by Hitchin in the 80s. In the case of 4-dimensional, you have this system that was done by Donaghey-Weinhold and Beasley-Heckman-Waffer in 2008. And well, since the introduction of T-branes, they gained a lot of interest in the literature. There's a lot of literature on this, and various aspects have been studied. They were used for phenomenology. Since these T-branes are, and they have non-commutative scalars, the space-time interpretation is not clear. Also, it's not clear how to encode this in the M theory dual to F theory. So this has been studied as well. We can use for conformity theories, uplift to the sitter. And now I would like to say that this can be used in principle also for black holes. So if you look at how Hitchin got this system, he was trying to look for solutions of the self-duality equations in 4 dimensions, but then with an isometry in 2 directions. So it took the gauge fields to be constant in 2 directions. So one can take this to the extreme and say, can we look for solutions where the fields are all constant? So if you throw away all derivatives, you can package all equations in this simple one, as was found the last year. And this equation actually already appeared in the past. It's the equation for longitudinal fibranes in the BFSS model. So one important thing is that this system doesn't allow any solution for finite matrices. So eventually, all the matrices that we will considering will be infinite. One can generalize this to the 4-dimensional case. In this case, you have many more equations, but the system is similar in spirit to the one I described before. So let me say a bit what the BFSS model is. It was introduced in the 90s as a fundamental description of M theory. So you have a Lagrangian, it's a quantum mechanical model, so there's no quantum field theory. And you have a Lagrangian that has this form, which basically comes as a system of n non-relativistic zero brane. So this n will actually take this to infinity in the end. So this model actually passes some non-trivial checks. You can actually see that quantizing it, you reproduce the spectrum of 11-dimensional supergravity. And you can compute interactions. Interactions appear only at loop level, but you can see that they coincide with the supergravity interactions. And you can construct membranes and 5-brane states. So this really looks like M theory. So we are interested in actually adding some D-branes in this system, and at least in the one motivated from T-branes. And the reason is that the black hole that we had before had some D-brane charges. So what we want to understand is how does the D-brane look like, and how can we identify the charges in the model. So one way is to follow the the literature on the BFSS model. You can use supersymmetry and compute the charges as center charges as was supersymmetry algebra, as was done by Banks, Schenker, and Seiberg. But here we are doing actually type 2A, so we can use what we know about the zero branes and try to compute these topological charges. And you can use Chern-Simons action, which was found by Myers in this case, and expand it and compute all the charges. So, for instance, the 2-brane charge has this form. The one which we are more interested in is the D4-brane charge, which has this form. And so far, so good. So how do we build the solutions? We can try to take some matrices pair of matrices that satisfy a Heisenberg algebra, something like of this form. You can see that this equation is not possible for real matrices because the trace on the commutator is 0. So you need to actually to really take infinite dimensional matrices. But this M, which is the size of the matrices, will actually take it to infinity eventually. And we can actually generate copies of the algebra. It's relatively simple by just taking tensor products, and this satisfies this algebra. N in this case is M to the number of copies, and this will be the number of the zero branes that we are actually putting in the game. So the answers we take is the form. It sort of looks like some sort of covariant derivative, where this is actually the derivative and this is the gauge potential. So the notion would be that the commutator will be some sort of non-abelian field strength. And so last was found in this set of solutions with D4, D2, D0 charge. And the zero branes are taken only to move in 4 dimensions. You have this solution. If you look at the linear coefficients in the X, this only give the 2 brane charge and some D4 brane charge. And the quadratic ones give only D4 brane charge. So eventually we only look for solutions with only D4 brane charge. So these are the kind of terms we are more interested in. And if you set to 0 all the linear coefficients, you can find also the number of D4 branes in this model. And you can generalize it and include a setup of D4 brane charges, which is the one we were looking at. So D4 brane that intersect at one point in the compact space. This is the kind of solution we have. It's similar to the one before, but yeah, it's a bit more complicated. The equations are more complicated, and so we want a more complicated setup. And in this case, we don't have any D6 brane charge, although in principle we can add it, and also no D2 brane charge. So we want to focus on a minimal solution and not try to add too much clutter into it. So at this point, I'll try to emphasize in several points that we really need to take an infinite number of these zero branes. But it's not clear, for instance, what happens to supergravity when we try to do this, because the back reaction of an infinite number of the zero branes can be brutal, and it's not clear how to treat this. But actually, what you see is that the charges that I wrote before in the supergravity solutions have, well, there are some factors that are not important for us, but you have the charge density that appears only, you have the number of branes, and the volume over which they spread. Also because what we need to do to build a supergravity solution is to take as mere solutions for all the D branes that appear. So it's only this quantity that appears, and therefore this is what we want to keep finite. So we want to take an infinite number of zero branes, but the density that appear at all points should be finite. So what we are doing actually really is to take, so long as we retain a finite number of D branes, the D branes will actually be confined in a finite volume. And then we take, at the same time, the volume and the number of D branes to infinity. And this gives the idea that Toft coupling, which we actually want to keep small, should be GS times rho, as opposed to GS times the number of D branes, which was the one that appeared before. So, well, more or less, I'm done with the talk. So let me go to the conclusions. So what I try to emphasize is that there are some complications with black holes in counting the entropies. That's because we don't know any CFD1 dual to ADS2. So there's been some activities in the literature recently. And what we would like to propose, at least, is that using T-branes, you can build some states that would be the microscopic description of black hole microstates in 4D. This should at least go to to black holes when you extrapolate a strong coupling. So taking this should suggest that at least for this setup, the BFSS model could be used to give a microscopic description. And one way to check this kind of proposal would be at least to do microset counting, which is a very difficult problem when you take into account the infinite number of matrices. And I would like to end it here, and thank you for your attention.
Thank you. Are there any questions? Okay. If there are no questions, then I have an announcement to make for all of you that coming for the dinner, for easing things up, it's better if you go and pay to Monica in the office B12, which is in the IFT ground map that you have in your folder, and well, you have seen it because it's next to the red room where we had the Blackboard talks this morning. Okay. So if you have this as change, she will be really grateful. And so if there are no more questions, let's thank Gianluca again, and let's go for coffee.